Hello everyone, I'd like to first thank you all for watching our presentation. Our project is the Seal Beach and Westside Wastewater Pump Station Replacement. My name is Jason Tran and we have Matthew Tem. We're recent graduates from the University of California, Irvine, and we're excited to showcase our project, which we worked really hard on. We'll have Matt start off our presentation with an introduction of the project, and then we'll get right into the technical details.
Hello, my name is Matthew Tem. We are tasked by the Orange County Sanitation District, OCSD, to design a new wastewater pump station in the city of Seal Beach, California. This new pump station will replace the existing Seal Beach and Westside pump stations, and if you look at the map, the Westside pump station is located to the north of the Seal Beach pump station, and they are connected via a gravity sewer system, shown in blue.
So the whole goal of this project is to design a new pump station that replaces the existing Seal Beach pump station and the Westside pump station. Also, we've been challenged with the goal of designing a dual wet well system built at different elevations, meaning one wet well would be higher than the other. Our goal is to identify the benefits of having these two wet wells like this and to see whether or not it would run more efficiently or it would reduce costs. So our project scope includes 6 main steps. The first step is to analyze the existing conditions regarding the existing pump stations, peak flows, and the configuration of the existing gravity sewer system. Step 2 is to design a new gravity sewer system connecting the existing pipe to the new pump station. 3 is to perform hydraulic analysis to make sure that our system will run efficiently and smoothly. 4 is to select pumps for our pump station. 5 is to design the pump station itself. And 6 is to calculate out cost estimates for the whole project.
The first task was to analyze the existing conditions of the gravity sewer and pump stations. When analyzing the existing conditions for the gravity sewer and pump station, we had to check that the values given to us by OCSD matched up with the record data. This included the peak flow rates, the pipe segments in the existing gravity sewer, the flow capacity, and to compare the original designs with current OCSD standards. Some of the constraints for this project include meeting minimum and maximum velocity requirements for the wastewater flow rate, choosing appropriate dimensions for the designs, as well as staying within OCSD property lines. The first step was to validate the peak flow rate given by OCSD. To do this, we were given existing flow data during a month of heavy rain, and using Excel, the average flow rate for each hour was found by averaging the data and moving along in increments of 1 minute. These values were then averaged again to find the largest daily flow rate, and this value was then compared to the flow rate that OCSD provided with us. The maximum flow rate we found from the data was 34 million gallons per day, MGD, which was larger than the 32.5 MGD given by OCSD. As a result, the design of the gravity sewer line and pump stations would be based on the larger 34 MGD. This is a basic diagram provided by OCSD of the existing gravity sewer line and the Westside and Seal Beach pump stations. After validating the flow rates, the existing system was analyzed and compared to current OCSD design standards. To analyze the existing system, we researched the as-built drawings from projects within the system and compiled the data of the pipe materials, slope, pipe diameters, and elevations. Using this data, as well as the Manning's equation, the flow capacity was calculated to verify that the existing pipe segments met with current OCSD, velocity, and D/D design criteria. Next, we will move on and talk about the steps involved in the design of the new gravity sewer line. Some factors considered when designing the gravity sewer include the routing of the flow, velocity requirements, configuration of the gravity sewer, and the cost of the project. For the pump station, 2 different setups were considered, a single wet well or dual wet wells. Our client, OCSD, asked us to look into potential designs that utilize a dual wet well where each wet well is at a different elevation. When determining the flow route for the gravity sewer, we had to look at the OCSD property lines and existing utility pipes and determine a location for the new pump station. The ideal fluid velocity range for this gravity sewer is between 2 and 4 feet per second to pick up and move solids, and an absolute maximum velocity of 10 feet per second to ensure safety during maintenance. For the configuration of the gravity sewer, we looked at the existing pipes and matched up the inverts and water surface levels of the proposed pipes to maintain steady flow when the fluid is transferred from one pipe to the next. A final criteria that was considered throughout the entire design process was to minimize the costs. This was taken into account by minimizing pipe costs, reducing the amount of earthwork, and choosing optimal pumps for the required amounts of flow. Here is a diagram of our proposed pipe design. The proposed gravity sewer line is shown in red, with the existing structures in black. The initial step was to determine the route for the gravity sewer, with the sources of flow coming from pipes 1, 3, 6, 8, 11, and 12. The routes considered were having the new pump station on the right side or the left side of the existing pump station, and after looking at the property lines and utility lines, it was decided to have the pump station on the right side. After creating this layout, we calculated the flow rates for each pipe using existing record flows that were provided, and using our calculated flow rates and the Manning's equation, we were able to test different slope and diameter combinations to find optimal pipe dimensions that met all of the standards, requirements, and minimized the costs. Our proposed design has 5 pipes. The proposed design will split the flow almost evenly between pipe A4 and the existing pipe 10, and each pipe will send the flow to one of the 2 wet wells at the new pump station. As shown in the diagram, pipes A4 and pipe 10 will cross, but the flows do not combine since these pipes will be at different elevations.
Alright, so in case you forgot, my name is Jason, and I'll be getting into more details about our pump station design, our pump selection, and our hydraulic analysis. Alright, so in this slide, we have a location map showing the project site. So as you can see, we have the proposed pump station right next to the existing pump station in the hatch. From what you can see so far, we're very limited in terms of how big our project site is because of the right-of-way at the Naval Station and because of the streets Seal Beach Boulevard and Westminster Avenue. So keeping that in consideration, we wanted to make sure that we minimize the size of the pump station, but also making sure that it's still ran efficiently. Alright, so here we created a 2D process flow diagram to show the system configuration of our pump station. Here, one pump is isolated to show the various components of the station. These components include the suction, the discharge, the manifolds, a meter run section, and the force mains exiting out the station. So all of our placement with our valves, reducers, and bends were all based on the design guidelines from OCSD. So we have the 2 wet wells on the left side where sewage is sucked out and the pump discharges it to the manifolds where all the other pumps are connected to it. The flow then enters a T and enters through the meter run where flow can be measured and data is collected. The flow then travels through the force mains and out of the station to connect to existing force mains outside. Our design includes blind flanges and isolation valves near the meter runs and the force mains. This is just to allow OCSD to use a bypass, in the case where emergency pumping is needed if there's too much sewage flow, or if maintenance is required, such as replacing that meter run. As requested by OCSD, we've also created a plan view drawing of our pump station. As you can see, it follows the process flow diagram that was shown before, where you can see the wet well, the suction, the discharge, the manifolds, the meter run, and the force mains. The dimensions of our pump station, again, is very limited, and we try to minimize the size of our pump station as possible. The dimensions for spacing between the pumps were determined to be at least 3.5 feet as per OCSD standards, and this is just to provide adequate spacing between the pipes and wall for ease of maintenance. Our layout for the proposed pump station is slightly larger than the existing Seal Beach pump station, but that's mainly to accommodate for larger wet wells and for a higher peak flow. And so again, that's kind of the reason why we're replacing this pump station, because the current one can't run efficiently because of an increase in the peak flow. And here we have a profile and cross-section view of our wet wells. We designed our wet wells to be an OG weir spillway, contrary to the existing free-fall spillway design for the existing station. The problem with a free-fall spillway is that over time, erosion occurs at the bottom of the wet well as sewage water falls onto the concrete. Here, the OG weir spillway prevents that issue. The slope of the OG weir spillway allows the wet well to be self-cleaning, which will reduce maintenance. We use the design guidelines of OCSD and the Hydraulic Institute's pump intake standards to determine the required dimensions of the wet wells. We took into account the design flow, the discharge velocity, and the suction inlet diameter to determine that a 40 feet long and 7 feet wide wet well will meet our design requirements. So next is our pump selection. So the reason why we decided to discuss which pump we selected first is because we did our hydraulic calculations in an iterative approach. We looked at various pump models and we did calculations for each of them to see what worked and didn't work. And I'll be getting more into details about that in a few more slides.